In previous lectures, we've discussed the relationship between different variables when at least one of them was a categorical variable. Now we're going to consider the relationship between two different quantitative variables. To get an example, let's go back again to our map of the world and to different facts and figures about the different countries and territories of the world. We've already considered the life expectancy in the different countries, and we've already considered which region these different countries and territories are in. Now we're going to consider two more variables. One is the average wealth of the country, or the GDP per capita for the country, measured in constant 2,000 US dollars for comparison. And later we're going to also consider the HIV infection rate, that is, what percentage of adults in those countries are infected with HIV. Now, you might think that the more wealthy a country is, the higher the GDP per capita, that might mean the higher the life expectancy as well. So how can we examine this relationship? Well, life expectancy and also the GDP per capita are both quantitative variables. One thing we could do if we want is we could convert the wealth variable into a categorical variable by just breaking up all the countries and territories into four different categories. That is the poorest quarter of the countries and territories, and the second poorest quarter, and the third poorest quarter, and finally the richest quarter. That gives us four different values for a categorical variable. And then we already know how to examine the relationship of that categorical variable with a quantitative variable like life expectancy. Namely, we can do the side-by-side box plots. So here we see a box plots for the life expectancy of the poorest quarter of countries and the second poorest and the third poorest and the richest. And looking at it, it does seem pretty clear that the poorest quarter of the countries, for the most part, have the smallest life expectancy, and the richest quarter of the countries, for the most part, have the highest life expectancy. So that suggests there's a relationship. But in a way, we haven't used the full information of the wealth variable. We've just divided up all the countries into four different groupings. So what if we wanted to use the full quantitative variable of the wealth, of the GDP per capita? Well, one thing that we could do is produce a scatter plot, as is shown here. In the scatter plot, each of the countries and territories gets a little dot where the horizontal axis illustrates the wealth, that is the GDP per capita, and the vertical axis illustrates the life expectancy. Now, if we look at it, it looks like just a crazy collection of dots, but we can start to see some patterns, and it does look like the countries with the highest wealth, the highest GDP per capita, also tend to have the highest life expectancy. We'll learn later how to fit a line of best fit through a plot like this, and if we put the line of best fit in, we can see that sure enough, it's moving upwards to the right, which is an illustration of the positive relationship between these two variables. The higher the wealth gets, the higher the life expectancy gets too. We can also compute something called the correlation between these two quantitative variables. Now, the correlation has a kind of complicated formula that's written here. It has to do with the products of the values of the data minus their means, and then we normalize it by dividing by the square root of the sums of the square deviations. So it seems kind of complicated. Well, one way to get some intuition about it is if the variables yi were actually the same as the xi, that is, if these two different quantitative variables were actually the same, or if they just differed by some sort of a positive linear relationship, as shown here, then the correlation would be equal to 1, to plus 1. And we'd say we have a perfect positive correlation between these two variables. On the other hand, if the yi's were the negatives of the xi's, or more generally had a negative linear relationship, then we could work out that this correlation would actually be equal to minus 1, and we'd have a perfect negative correlation. All the other correlations would be somewhere in between minus 1 and 1, and they would illustrate the extent to which the variables either increase together if the correlation is positive, or one increases and the other one decreases if the correlation is negative. We should also remember that correlation, like lines of best fit, only captures the linear aspects of the relationship between two variables. In some of the examples we're considering here, there are also nonlinear effects which aren't captured by the correlation or the line of best fit. So what about for that life expectancy and the wealth of the countries? Well, in that case, we can compute the correlation. And we see here that it is indeed positive, and it is indeed pretty high. It's not 1, but it's getting up there. So this shows that yes, indeed, there is a clear positive relationship between the wealth of a nation and the life expectancy of a nation. For another example, let's consider that variable of the HIV infections, specifically what percentage of the adults in that country have HIV. In this case, we might expect that the more HIV, maybe the worse off the country is and the lower the life expectancy is. How can we test that? Once again, we have two quantitative variables, in this case, life expectancy and the percentage of HIV infections. Once again, we can do a scatter plot. In this case, the scatter plot shows on the horizontal axis the percentage of HIV infections of adults in each of the countries and territories, and on the vertical axis, the life expectancy of that country or territory. Well, once again, we see the dots are kind of all over the place, and it's a little hard to make sense of it, but once again, we can see that there is some sort of a relationship. Indeed, in this case, we can see that the countries which have the highest percentage of HIV infections, sure enough, tend to have the lowest life expectancies. So this suggests a negative relationship, as we might have expected, a negative relationship between HIV infections and life expectancies. We can also compute the correlation coefficient, again, as we did before. And in this case, when we work it out with that complicated formula, or get the computer to do it for us, we see we get quite a negative value for the correlation as shown here. So this illustrates that, as we might have expected, when a country has more HIV infections as a percentage of adults, it probably tends to have a lower life expectancy too. We'll come back to these relationships later on. For now, let's look at one final example, this time with our old friends the skeletons once again. In this case, remember, one of our main variables was the difference between the estimated age of the skeleton at death and the actual age of the skeleton at death. We might wonder, what other variables is that influenced by? Well, one is the body mass index, or the BMI, of the person at the time of death. We might think that if the person was heavier, had a larger BMI, maybe that made it harder to estimate their age, or maybe easier, or maybe it made the estimates tend to be too large or maybe too small. We might not be quite sure, but we might think there's some relationship. Well, now we know how to test it. We can once again draw a scatter plot. And here's a scatter plot where the horizontal axis is the BMI, the body mass index, and the vertical axis is the difference between the estimated age minus the actual age at death of the skeleton. Looking at this scatter plot seems maybe the most confusing of all, because there's dots all over the place. Well, once we learn how to do lines of best fit, then we will be able to see that in this case, the line of best fit is sloped slightly positive. So it means that when the BMI gets larger, then the age difference tends to get slightly larger. We can also once again compute the correlation coefficient, or let the computer do it for us. In this case, we get a correlation which is equal to 0.136. So it's not large, it's fairly close to 0. But it is a little bit positive, so once again it suggests that when the BMI gets larger, then the age difference also gets a little bit larger. Now we'll return to issues of relationships between variables throughout the rest of the course. But for now, we can see that using such concepts as scatter plots and correlation, we have our first understanding of the relationship between two quantitative variables.